Okay, hi and welcome to video notes on geometric sequences. If you've been following the video sessions, yesterday we talked about arithmetic sequences. And arithmetic, the pattern that's generated between each of these terms is going to be addition and subtraction. So that's how we would move between them. In today's notes for geometric sequences, our pattern that's going to be between our values is going to be either multiplication or division. That's how we're going to move between these. And the term that we like to use for multiplication and division is generally called a ratio, meaning it's both. So when I use the term ratio, I'm going to refer to it either being multiplied or divided. So a geometric sequence then, by definition, is a ratio of any term and its preceding term, to its preceding term, that's constant. Should be the same ratio each time. That's what makes it a pattern. So what does that look like? Well, it kind of looks like this here, a to the ar squared to the ar cubed. What does that mean? It means each time that I move between there, there's a multiplication or a division of that ratio. And each time we do it, that ratio gets multiplied or added on again. Well, sequences or multiple times of multiplying by the same amount means that we start using exponents. So that's twice being multiplied, that's 3 times being multiplied, the next one would be 4 times being multiplied. So that's what worked. If we wanted to find out what that ratio was of this sequence, then we would take, like we've done in the past, now we've done this, we took y2 and divided by y1 and found the common ratio. That's what we've done in the past. Well, this time, because we're talking geometric sequences, we're going to say it's a2 divided by a1. So you take the term that you're looking for or looking at, and you divide it by its preceding term, the term before it. If we do that, just to see how that comes out, if we take AR, looking at the second term, dividing by the first term, its previous term, the A's cancel out, leaving just an R. Same thing happens when we do the third term divided by the second term. The A's cancels out, and the R's are also divisible, or a subtraction of the exponents, meaning that turns to 1 or R, and that continues on. What we find out with any time that we do our divisions, like we said just a minute ago, is that we're going to get what we call the common ratio. That really should say A to the 2 divided by a to the 1. But anyway, that's what we get is the common ratio. All right, so let's take a look at some examples here. Okay, so the first example then is a couple sequences, a few 6 sequences here, and we're supposed to decide if they're geometric or not. In this case, it's geometric or not. We don't care what the other ones are, but you'll notice on some of these other ones that I've left up here, I've noted that they were arithmetic. You will eventually have to decide if they're arithmetic or geometric, so I added that in. But if we do identify it as geometric here, then we need to find that common ratio and identify it, which is just the constant value that should be divided, or the ratio that comes up between the division of two terms. So let's take a look at this first one here that we're going to look at. Number 1 says that we would take 15 in this scenario, the first term we're looking at, and then divide it by its preceding term. So 15 divided by 5 is 3. That's great. Let's do the next one. 45 divided by 15 this time, right? Its preceding term is 15, is also 3. So this one looks to be, and you can take 135 and divide it by 45, you'll find out that it's also 3. So that's where we get our R value. That's how you'll find R each time that it asks you what's the common ratio of this geometric sequence. Well, divide them. See if it's constant. If it is, that's your ratio. So yes, it is a geometric sequence, and our common ratio is 3. What happens if it's not? We already know this one's not, but what happens if we did that? Well, we would start out, if we knew we were looking for geometric, we'd take 30 and divide it by 15. Well, that comes out to be 2. But if I do the next one, which is 45 divided by 30, I'm going to note that that's not going to be 2. I don't even need to do the calculation. So right away, I'm going to know it's not geometric. If you go back, and if you would want to know that it's arithmetic, you can see that we would do a subtraction between these two, right? We would do, let's use a2 minus a1 in this case, so it would be 30 minus 15, or 15. And then we would do the next one, which would be 45 minus 30, or 15. And that would be the same thing for the last two terms as well. So it is arithmetic. It's not important for this question, but eventually it will be. So there's one more let's take a look at here in this sequence thing is, hey, Mr. Hallam, what happens if I got a bunch of fractions? Now, I'm not scared of fractions, but I know to be cautious with them. Well, let's just remind ourselves of what fractions rule might come into play here. Remember that when we divide, because that's what we'll be doing, correct? We'll be dividing a2 by a1. So instead of dividing, we multiply by the reciprocal. What's that look like? Well, this would be a division of 1/2 by 3/4, which we don't do, right? Instead, we take the reciprocal of the divisor and multiply it. So we take 1/2 and multiply it by 4/3. So let's implement that over here on this example. I'll blow it up so I get some more room. So first thing that I would probably do here is I'm going to change this integer 4 into a fraction form. Still an integer, still a whole number, but now I got it looking like a fraction so that I can complete my a2 divided by a1. So this is going to be my a2, which is my 8/3, the term next to it, right? So I'm going to take 8/3, right? So I'm doing those two. And instead of dividing by 4, I'm going to multiply by the reciprocal 1/4. Well, we can go ahead and reduce because this multiplication is going to reduce a little bit here, right? 4 divides into 8, and it's going to leave a 2, and 4 divides into 4, 1. Once. So if I multiply across, and that's what we do when we multiply fractions, numerator to numerator, denominator to denominator, I find out this results in 2 times 1, which is 2, and 3 times 1, which is 3, or 2/3. So let's do that at least one more time here. Let's take these two terms and do the same thing. So I'm going to take 16th ninths and then the preceding term, which is 8/3. So I'm going to start with 16 ninths. And instead of dividing, I'm going to multiply by this reciprocal, or 3/8. Okay, again, there's some reductions to be had. 8 goes into itself once, 8 goes into 16 twice, and some reductions this way as well. 3 divides into itself once and divides into 9 3 times. So I multiply across, 2 times 1, 3 times 1, I get 2/3. And as you can guess, the last one's going to work out to be the same way. So our ratio is 2/3, and yes, it's geometric. Okay, so let's jump to the next page then. Here it is. There are two formulas that we can use with a sequence being geometric. But let's recall before we look at those what we have a little bit for the arithmetic side. On the arithmetic side, if we had a recursive formula, we said that any term that we wanted to find, right, we would take the previous term and add the difference. So in the recursive formula for a geometric sequence, then, we've got something very similar. What term we're looking for, right? We take the preceding term or previous term, and instead of adding and subtracting like arithmetic is, geometric is multiplying and dividing. So we're going to multiply by a common ratio instead of adding a common difference like in the arithmetic. But notice they're very similar. Remember that for recursive, that they are really only good for the next term. So if you needed to find the 100th term of something, you'd have to do the recursive nature or do each calculation multiplied by r 99 times. So this is only good for short sequences or if something that's like 6 or 7 terms that you don't have to do a lot of calculations for. Which brings us to the next form of a formula for a sequence, which is explicit. In the explicit form, remember, it's good for any term anywhere in the sequence. So when we do this one, this is what it looks like. What term we're looking for is going to be equal to its first term. Notice the difference there. The first term times the ratio, and that's going to be raised to the n-1 power. Okay, so that's what we're going to use if we're going to do explicit. Remember, a1 is the first term, an is the term you're looking for, n is the number of the term where it is in the sequence, and then r is the common ratio. Okay, so let's move down and try some examples here. So if we look at the first example, example 7, our first term, oops, erase those, we'll write them back in here. Our first term in this sequence, right, is a to the first, right, a sub 1. That's our first term. Our second term is a sub 2. You can see that this x here really kind of represents n. It's the number in the sequence of the term, and then the actual term values is 5 and 10. This looks like an XY table because it is, but I just kind of wanted to relate the two so you can see how it looks as a sequence and then as it looks as a function. So now we've got a kind of understanding of our table here. Let's go ahead and see if we can break this down. We know that it's geometric. So if it's geometric, what we know then is that a sub 2 divided by a sub 1 should give us our common ratio if it's the same all the way down. So let's go ahead and do that. 10 divided by 5 is going to be 2. 20 divided by 10 is also 2. And 40 divided by 20 is 2. You know that this means that this is geometric, right? And that it's a sequence. This also gives you your r value, which happens to be your b value in exponential form. And in this case, it happens to be 2. So if we wanted to find the next term in the sequence, or a sub 5, this term right here, we're just going to take the previous term, multiply it by 2. Kind of what the recursive formula says, previous term times the ratio, or in this case, 2. So we're going to take 40 and multiply it by 2, and we're going to find out that that's going to be 80. Now that we have that as 80, let's see if we can actually write that recursive rule. Remember, the recursive rule is whatever term you're looking for is equal to the previous term times the ratio. So the recursive rule is actually pretty easy to write. We say it's the previous term, because we don't know which term we're looking for. We'll plug that in when we figure out what term we want to find, times the ratio, in this case, 2. The explicit rule is whatever term you're looking for is the first term in there. So we're going to have to look for the first term, which isn't hard to find because we've already identified it. There's that 5. And then we go ahead and multiply that by the ratio, and then we raise it to the n minus 1. Again, n's the number of the sequence, so we don't have to plug anything in there. So our first term happens to be 5, so we're going to write 5 times the ratio that we have is 2, and then we're going to raise it to the n minus 1. Now that is an exponential function in a geometric sequence form. We can change that so that it actually looks a lot similar to what we're used to as an exponential. I want to note though, what we're doing is not necessary by any means. I just want to make a quick connection here. You'll notice though, these are almost identical. We have an a value, we have a ratio, we have an a value, we have a ratio. The difference is we have an exponent of x here when we have an exponent of n minus 1. Remember what I said, that sequences begin at the first term, where functions begin at the, let me change my color so we can see it, at the 0 term, or the y-intercept, if you will. So to make this look like a function, we really need the function to begin one back on the sequence. But what does that really mean? If going down the sequence, we're multiplying by 2, to go back up the sequence, to go one term back, we're going to divide by 2. Or specifically, we're going to divide the first term by 2. So we take this 5 here, let me change my color back to the right one, and we say a sub n is equal to 5 divided by 2 moves us back up the list 1. Our ratio still stays 2, but guess what? Instead of n minus 1, we have n, because we moved back up the sequence 1. Again, this is not necessary. This is really just to make a connection. All right, let's move down here and go check out some more examples, 10, 11, and 12. Okay, and this is the first example here, number 10. It says, write the first 6 terms of the geometric sequence in which they give us the first term, g of 1, is equal to 6, and our common ratio is equal to negative 2. Now, I know they switched it from a sub 1 to g sub 1, but that's fine. We do that all the time with functions. We switch what they mean. G of 1 is the same thing as a sub 1. All right, so let's write down our recursive formula. Well, actually, let's put recursive down. The reason we're going to use recursive is because it's only 6 terms, and all we have to do really is multiply this ratio 6 times. We wouldn't need to do an explicit one, plus it wants us to see all 6 terms. So that's another reason that we're going to use recursive over explicit in this one. So here's our recursive formula, our previous term times our ratio, and let's write down the other piece of information that they give us, which is a sub 1 is equal to 6, and I guess we should write down that r is equal to negative 2. All right, so to find the second term of the sequence, because they give us the first one, we're going to do exactly what our formula says. Previous term, which is a sub 1, is 6, and we're going to multiply it by negative 2, which is going to give us negative 12. To find the third term of the sequence, previous term, or a sub 2, because we're finding a sub 3, so we'll write negative 12 this time, times the common ratio of negative 2, and the two negatives are going to make a positive, leaving us a positive 24. Again, same sequence. A sub 4, we're going to need the previous term, which happens to be 24, a sub 3. So we're going to put in 24 here and multiply it by that ratio once again. So we're going to get negative 48. And I did a sub 5 and a sub 6. And this is a nice way to see your work. Again, once we get out of this and you take your quiz, what you'll do is you'll say, oh, the first term is 6. And then I'm going to multiply that by negative 2, a negative 12. And then I'm going to multiply that by negative 2, positive 24. And you're just going to move down the sequence. But for the quiz, so that I can see that you know what you're doing, I get to see this. Okay? So that's the sequence that it asks for, written as a sequence there. Looking at question number 11, though, notice they say just find the single eighth term, which is a good way to say use the explicit. I think they tell us to use it right there, actually. But this time they've given us G2 instead of G1. That's fine. We can work with that, except for the fact that I've got an A sub 1 written right there that we'll change to G sub 1 so that it looks appropriate. All right, and they give us our common ratio as negative 3. So we list our G2 is equal to 6. We list our common ratio. But to do this for explicit, notice we do have to have the first term of the sequence. The problem is we've only got the second term of the sequence. So what we're going to do is we're going to use the fact that we know that and actually use a recursive formula to go backwards for it. So we know that G2 is equal to the previous term, right? The previous term is the one we don't know, which is G sub 1. And it's going to be multiplied by the common ratio, in this case, of negative 3. But what we do know in this one is we do know what G sub 2 is. So we're going to change that G sub 2 to 6. And we end up with this. 6 is equal to G sub 1 times negative 3. we've written ourselves a little inequality here. And in this equality, we have one unknown, which means that we can solve it. So we're going to solve this by go ahead and dividing by -3 to both sides. And 6 divided by -3 is -2. And we find out that g sub 1 is -2. Now we can write our explicit form. So I'm going to take -2 here, plug it in for my g sub 1. And this really, I don't know if you caught that, I just finally caught that, should be our ratio there. So now we've got -2 times our ratio, which is -3 to the n minus 1. We're done. It asks for the explicit form. So there's our explicit formula, but now what we're going to actually do is plug in 8. So right here, instead of n, so because I don't have a lot of room, I'm going to plug in 8 instead. I just erased it and rewrote n. So we're going to plug in 8 minus 1, right? 8 is the term we're looking for. That's the end. It goes right there. So you're going to calculate that out to be -2 times the ratio of -3 raised to the 7th power. So calculate those first. -3 to the 7th power. It'll be a negative number, and then multiply that by -2. You're going to find out that it's 4,374. All right, let's move down to our last example here. This is a word problem. It says the Floyd family starts saving for vacation that is 1 year away. They start with $125. Each month they save 8% more than the previous month. How much money will they have saved 5 months later? Now we could write this as a exponential function, a times b to the x. But let's practice using our explicit and recursive formulas and see that we can do the same thing with those. So let's start listing our information. First piece of information is that they start with $125, which is not that they save some money and then have $125, meaning the first change in the sequence. This is before the sequence begins, which to us means that it's a sub 0. Okay. Then we also see this percent here, and we know that that's usually our b, right? Or at least the calculation for b, 1 plus our rate. So well, it's pretty small. Let me rewrite that so it's a little bit bigger. So that means that our b then is equal to 1 plus r, because we're familiar with that from our exponential functions. So that's where this comes from. Let's go ahead and calculate that percent then. So we're going to have 100% of the original plus the decimal form of 8%, which is 0.08, right? We move it 2 places to the left, 0.08, or that turns into 1.08. So now that we've got that, we really need to find the first term to be able to write the explicit form. So to write the first term, we're actually going to use our recursive sequence formula. The reason we're going to use that is because we have the 0 term, and all we have to do is take that 0 term, which is the previous term if we're looking for a, and multiply it by the ratio, or it comes out to be 135. So we used our recursive formula to advance the sequence one ahead. Now we've got a to the first, which we can plug in to our function here. So let's write it right underneath here. A sub n for our explicit formula is 135 for our first term. Our ratio is 1.08, and then it's n minus 1. So if we want to find a to the 5th term now, we're going to rewrite 135 times the ratio of 108, and we're going to put 5 in here, or 5 minus 1, which is 4. If you take that 1.08, raise it to the 4th power, and then multiply all of that by 135, you're going to find out that your value is 183.67. All right, so now that we've got that done, we've seen all the examples. Let's just recap quickly. We've got 2 main forms for a geometric sequence, right? We've got a recursive, the previous term times the ratio, and we've got our explicit, which is good for any term in the sequence, our first term times our ratio raised to the n minus 1 power. Additionally, remember that the difference between arithmetic and geometric is arithmetic is an addition or subtraction between the pattern, between the terms of the pattern, and geometric is a multiplication or division between the terms of the pattern. And don't forget that provides us our common ratio. All right, good job today. We'll see you in class. Thanks for watching.